Welcome to the Copernicus Data Space Ecosystem webinar with a focus on machine learning using openEO. The topic will be presented by Jeroen Dries, a product lead of openEO at VITO. And without further ado, Jeroen, I give the floor to you.
Hi, thanks for the intro. So no need to introduce myself then. This webinar will be about machine learning in openEO. And it's going to be a bit of a deep dive into the topic. It's more advanced than some of our other introductory webinars. So we do assume a little bit of knowledge on openEO, but don't worry if this is the first time you see it, because there's also sufficient general information in here to get something out of it without being an expert already. That is the whole idea. So machine learning is one of the many features in openEO. And actually, we have a long history of applying it at scale. This happens to be the case because machine learning is really a key use case or a key technique, I would say, in Earth observation. You typically use it for land cover maps, we use it for crop type maps, and actually all kinds of classification problems can be solved using machine learning. And that's why rather early on, already in 2022, we produced our first continental scale crop type map as a demonstrator back then. And this quickly was followed up with a real life map on a larger area, so EU38, all 38 EU countries, in fact, and then for 5 years. So this was real continental mapping at scale on openEO. And of course, if you do continental, the next step is to go global. And that is what we are effectively doing right now, producing global maps in two key projects, ESA WorldCereal and the Copernicus land cover and forest monitoring service. And to enable all of that, we really have always had a strong focus on cost-efficient production. So that is, really a lot of what we do in openEO is under the hood, making the same machine learning process always faster and faster by, for instance, optimizing the I/O performance, but also how we deal with the cloud. openEO is a system that runs on the cloud where the Copernicus data archive is natively hosted. So we have a whole lot of options to maximize the efficiency of cloud usage for our users who, in fact, do not even need to know how we are doing all of that. And that is the other big key thing of openEO, that we focus a lot on ease of use. As you will see in the webinar, the code is not about using clouds or scheduling workers. It's really describing the machine learning workflow and the data that you want to use in it, rather than dealing with the technicalities and the IT part of the job. And then there's a bunch of other things that openEO does, and one main thing for sure is adhering to FAIR principles, so that the maps you generate already come with the rich metadata as prescribed by FAIR principles. And that is actually also very useful if you want to release maps really to the world. So that is why we have been focusing a lot on this static map production. But there is actually more to it than static map production. A new thing that is happening, that we are seeing, and that is possible with openEO, is to offer it in an as-a-service kind of concept. And the use case here that we see is actually coming from the ESA WorldCereal project. They were doing static maps a lot at first, but then you have long production times. Little opportunity for tuning your crop type map to the region that somebody is working in, because you use one machine learning model that is applied globally. Also, it's based on purely publicly available training data. And in some parts of the world, there is no training data, and that affects the model quality. And then as a user, if you're looking for a very recent crop type map, then usually it doesn't exist because of these long production times. So what is WorldCereal doing as a solution? They turned it into a dynamic mapping service on top of openEO. So using the same code that you'll see in this webinar that generates static maps, they are also able to offer it as a service. And then the user can generate maps on demand. That's one thing. But they can also train their own model with private training data that is relevant for the region in which they want to generate crop type maps. And that helps the accuracy. For timeliness, of course, they can just produce it when needed or when the growing season allows it. And all of that runs for free, between quotes, on CDSE. Because CDSE takes the operational cost of running this huge cloud-based processing service. The user of WorldCereal only needs the public service, which comes with quota, to generate maps. And that is another nice example and the reason why our users, our projects, actually implement their machine learning workflows on top of openEO to gain this extra flexibility. So that's a little bit a big motivator actually for using doing the machine learning in openEO. This is how the WorldCereal workflow looks like. And it's actually quite representative of other things. So it's a great introduction to what we'll also be seeing in the notebook. So it's always this very same steps. You load a bunch of data that's pre-configured, or like these data sets are already there and configured for you. WorldCereal is based on Sentinel 1 and 2, an elevation model, the Copernicus DEM, and the meteo data, the ERA5 meteo data. Then all of that loaded data gets pre-processed into features that are used by the model to perform inference. So the features are there to predict the classes, the crop type classes. And what is really innovative about WorldCereal, in fact, is that the feature computation is based on a foundation model. This foundation model is called Presto. It's developed at NASA Harvest. And it's a foundation model that takes an Earth observation time series, like Sentinel 1 and 2, and then is smart enough to convert that into a set of features, which can then be used by a standard CatBoost-based classifier. And that's how crop type maps are created in that project, which is really state-of-the-art and which is also possible in openEO. In the notebook that I'll show today, the feature computation is really using much more the classical approach, which is interesting because then you can see like how you can do it using just plain statistics. And of course, not the kind of black box approach that these foundation models take. But still, openEO allows all these techniques and does actually allows comparing the comparison that you get out of using any of them. So that's the WorldCereal project, which is a happy user of CDSE. So without further ado, let's dive into the Jupyter notebook that we prepared. There's a lengthy URL here, but in fact, it can most easily be found on the website, on the CDSE documentation portal, in fact, is what I'm showing here. And then you go to Jupyter Notebook samples. And under land monitoring samples, there's actually the one that I'll be showing here. For the sake of my demonstration, I am going to switch to my local Jupyter notebook environment. So all these notebooks are available on GitHub. You can download them locally, or you can use them on CDSE, Jupyter environment, and then try running them yourselves after the webinar. That might be needed and is very much recommended if you really want to gain a deeper understanding of how it works. So the notebook will show, it's called dynamic land cover mapping, because it applies this dynamic concept where the user of this notebook wants to train a model himself. How does land cover mapping, let's take a step back. With a general overview, like a blueprint, if you want, of an ML application. We also kind of saw it just with WorldCereal, because you always have some recurring steps. You usually start with data pre-processing and fusion, where you load Sentinel-2 and do cloud mask and fuse it with Sentinel-1. This step is the same for each activity in your process of training a machine learning model and applying it, because it has to be the same. The inference step on the right here needs to run on exactly the same data as was used for training the model, which makes a lot of sense. But then actually for the training part, there's a few options that you have that we try to show here. In case you can train the model on points, and that is what we do here, it's using pixel-based information, but over time, so that you have the time profile of a given pixel as very much the basic input that you'll use to predict the land cover type in this case. In that case, there's an aggregate spatial method in openEO that allows extracting point data. And then if we train a model in openEO, we will use the built-in random forest process and then immediately generate a model. That's the fastest approach. But it's also possible that you actually extract the points into a tabular format, like CSV or Parquet, that you store it. And then what people do is they take the tabular feature info and perform the training offline. This is, in fact, what allows projects like WorldCereal to train much more advanced models that are not part of openEO. Because openEO contains random forest, that's really a very good basic kind of method, like a classroom method if you want, but it's already a bit older. It's not the most advanced one out there, which is why this offline training is relevant. Now, let's say you want to go even more advanced and you want to include contextual information, then we also have the option to do labeled patch extraction. And then we arrive at this filter spatial method, and you generate a whole bunch of netcdf files on which you can also perform offline training. That's how you do training and how you extract Earth observation features into a local data set for offline training. Once that is done, you go to inference. This is map generation or validation. And there we have usually the most common options in openEO, or one method is simply predict random forest, or people use apply neighborhood. This diagram really just tries to give you some pointers where to look for depending on what you're doing. So that's the general picture to have in your head before we go a bit deeper. So let's do that. And let's look at this first process of data fusion and pre-processing. Here, it's all going to happen in the next cell, and this is like basic openEO usage. But I will walk you through it, right? It's basically the shortest pre-processing workflow that you can imagine, but still it's a substantial thing because we do have quite a bit of input to our model. It's not a trivial example. The first thing at the top here is basically loading and cloud masking Sentinel-2 data. That's the basis of everything. And then we will compute a bunch of indices. You saw here that we defined some indices. And openEO makes this easy because there's a built-in method and a predefined list of indices that we know, and you can immediately compute them and combine them with the original spectral bands. That's it. Those are our indices. Then, yeah, of course, Sentinel-2 data is rather random depending on the overpasses. So we want nice 10 daily values, and that's done using this aggregate temporal period method, followed by linear interpolation to get rid of no data gaps, which may still happen. This is compositing, but it's on a 10 daily interval. So it will happen that in Sentinel-2 you have gaps, and we fill them with a simple interpolator. For the Sentinel-1 then, it's similar, but there we still need to compute backscatter, and that's done using this line. With a single line, we just compute backscatter in openEO on the fly. We apply a filter on orbit direction because, especially in Europe, there's usually enough data in one orbit. And then instead of computing the indices using a predefined method like we did in Sentinel-2, we compute a ratio ourselves. So as you can see, there's this lambda here, which is a function which will be applied over the bands. That's why we specify bands, and which takes the first band and divides it by the second band to get a ratio. We also maintain the original bands, but just to logarithmic transform. Then we're already done, and we do the same thing, do a temporal composite and some linear interpolator for gap filling, although that will be less in Sentinel-1. And those are our two really basic data cubes for input. I think they're also shown a little bit lower right here. Those cubes will be merged, but only after computing some statistics, and that is in this final method here. Let me not scroll too much, but this is actually the main thing, this compute stats. And we use built-in functions to compute 3 quantiles for these values, the standard deviation, and then extract simply some time steps actually out of the whole time series. And this is a crucial thing because random forest does not work with a time dimension, right? It, as input, as a feature vector, it takes a one-dimensional input. And before this step, we had bands and a time dimension, so two-dimensional input. And this magic step right here is where we transform the time dimension, where we basically flatten it to convert it also into bands. And then we just have a data cube with locations, X and Y, and bands. And those are what we call in machine learning, what we call the features, which will be used by the classifier to determine what classes they are. And then depending on the use case that you have, like here it's land cover, but there's others as well, you would typically use different features. You would use different indices. For vegetation, it's common to use vegetation indices, of course. But if you would be detecting water, then you would use an index that is good at showing whether something is water or not. So we have our features, and that's the whole pre-processing. That was like probably the hardest part of the whole notebook, because now we arrive already at the training part. And as you can see, it's way shorter. So we load our features. It's a function, so that's fast or short at least. We have training data available in the Lucas training data set for different points and polygons in Europe tells us what the land cover class is. So we have in the beginning of the notebook, I skipped over that, we have loaded this Lucas training dataset as a local data frame. And here we converted, again, we convert the geometry to JSON points to extract our features at those points. And then when on those extracted points, when we are going to fit our random forest model, we also provide the target labels that go with it. And then you really have all the necessary information. And we can actually train the model. In openEO, up until this point, nothing really happened. No computation at all. It's only when we do this create and start job that we effectively run a computation, or in this fact, a model training. This takes a little bit longer, so I did it before the webinar, as you can see. And this is the metadata that comes out. We can see that it took a little bit under half an hour to train the whole thing, and that it cost me 75 credits on CDSE. I'm not sure if people are aware, but on CDSE, every user of openEO gets 10,000 credits on a monthly basis. So for this type of model, I can run really quite a lot of training jobs until I'm happy before I would be spending my public quota entirely. There's also some other metrics for, this exercise. They don't really matter. They mostly serve for comparability between jobs when you are doing multiple things in openEO. The thing shown right here is a bit more interesting. Not sure if I can see it. Yeah, there we go. This thing with the boxes and arrows, it's what we call in openEO the process graph. And it's really all the steps that I have shown above in Python code, but then in a different representation, and in fact in the representation that openEO uses internally. So it's really openEO defining all these processes as boxes and defining all the links between them. So this is a standardized description of your pre-processing workflow. And eventually, all the way at the end, we see that we actually did the random forest training. And this is the standardization that openEO offers. So if another backend, which follows openEO, then actually you can send the very same process graph to it as long as it implements the same list of processes. And most of these processes are really part of the core standard. In fact, only the random forest itself is newer and probably somewhat less supported. But still, it's a nice example of standardization. So we have our model. Then what a data scientist would typically do next is wonder, okay, of course I was able to train a model, but how good is it? What is the accuracy? To establish that, we actually go back to our pre-computed feature data cube that we have anyway already in openEO. And we want now to run inference on it. So we are going to run the model it, but for points where we already have the output data. So we have validation points where we know the landcover label. We run the prediction on random forest using our newly trained model, and we extract the points to a CSV file. So this is another openEO job that we run, and that then runs. In this case, it took 20 minutes to get some points out of it. We download the CSV file locally. That's what actually is happening right here. And then we can do a nice confusion matrix. And this is all just using plain Jupyter Notebook, right? Just scikit-learn and so on. To get it as a single number, we can get the accuracy score out, which seems to be 85%, which is good enough for us and makes us quite happy. So that's how you do a validation step, which is actually really very, very similar to how you do the actual mapping step, which we typically call the inference. And it's what the last thing we actually show here. It's again the same, using our complex feature computation functions. That's where we had all the statistics going on, the Sentinel-1 loading, Sentinel-2 loading, and so on. It's important that the time range is similar, and that is actually, this is somewhat region dependent because different regions of the world have different seasonality. But most important is that it's the same, the length of the time period is the same. Otherwise, we will be able to just happily compute statistics over the period, but the feature meaning will be entirely different, right? And the model will not work. So this is key, that we are looking at the same period, at least where the land cover is also behaving in the same way, which is especially relevant for vegetation, of course. And then we specify the area on which we want to run, and again use our predict random forest, where we pass in the information to openEO where it can find the model. This then again ran. My job took only 12 minutes here to compute this small map. And then if we plot it right here, we see that we got some land cover out. In this very simple example, we focused on getting out only these 3 classes, and those are the ones you see here on the map. And that's it. That's a full map production. If you're interested in, okay, how do this is showing me how I can do it for a small area, but now how do I make it run on a larger one? Then we have separate notebooks and tooling for that. And I put the links in the notebook so that people can find them. And basically what it comes down to is defining a grid, and that just running multiple jobs over each cell in your grid using the openEO tooling. So then you really run a lot of jobs, and you can generate a map for full continents or even global. So we provide the tooling for it, and using it is very much recommended, in the sense that often people try to write a regular for loop, but then they discover that, for instance, if there is a network issue and you can't reach the backend, then your script fails. And this tooling, this has all the robustness implemented by design to avoid such failures exactly. For my last job that I ran, I also want to show the openEO web editor, which I also use quite commonly. And as you can see, it keeps track of all my jobs. It allows me to see my jobs. And just as I was showing metadata in the notebook, I can inspect the job that generated my land cover map. It was a very small job, so the credit cost was in fact lower than the cost of training the model. That's simply because I was running it over such a small area. You see that I again have the metrics, the process graphs, and very interestingly, like this is the asset. This is my actual land cover map. We have statistics in there, some nice metadata. This is stack metadata, by the way, for those that are familiar with it. And what we also include are all the input products. So you really see a whole bunch of Sentinel-1 input products coming from CDSE that were included into this map, and then a whole list of Sentinel-2 products. This Sentinel-2 is a little bit longer. That all was included in this map. And this provides for some nice traceability. Those are those famous FAIR principles again, having traceability to the source data that was used to generate a certain map. Let's see, anything else to say here? I don't think so. If needed, worst case, something goes wrong, I can click on the logs button and fetch me some logs. This is usually a whole bunch of text that comes out. So this is really for debugging purposes, and it's what we use. Also containing performance metrics, for instance. And what I also sometimes like is the preview functionality. Unfortunately, it's a bit black and white, well, grayscale, in fact. So I can zoom in on my newly generated land cover map. You can see it's a very small part of Belgium that I generated here. And there's also a button to actually share my metadata, my work with others. So it's a convenient tool to explore altogether. Okay, that was it for the notebook. Then I have one more thing that's slightly more advanced, but I still wanted to share it because I showed the WorldCereal example, which uses foundation model, which is quite a bit more advanced compared to random forest. And I still wanted to put you on the right track of how to do that. I slightly touched upon it because it's using this apply neighborhood method. And the Python user-defined functions. User-defined functions is an openEO feature that allows you to run arbitrary Python code over your data cube. And apply neighborhood is the process in openEO that says on which area of your data cube you want to run a certain function. And with the settings that are shown here in the screenshot, it would run over all time steps, all bands, and then an area of a certain size, even with an overlap between chunks to allow you to get better continuity of your classified map. That is apply neighborhood. And you see a reference here to ONNX. And this is a very nice format. Because it's from Microsoft, it's not from us. It's used in the machine learning world as a portable general format to encode machine learning models. Because otherwise, you know that there are a lot of libraries like TensorFlow and Torch and so on. And then you need to deal with all of them like separately, and they have different dependencies and whatnot. And what this example in UDF shows is how to load this ONNX model, which can be created by converting a TensorFlow or Torch model, or even things like CatBoost, into this common format. And yeah, as openEO is all about standardization and making scientific workflows portable, ONNX is really a great match for that. And we think this will allow us to do even more interesting things in the future, where we can even support it natively rather than as part of Python code, which is exactly what is actually shown here. I'm not going to go too deeply over this one, also to allow sufficient time for questions. But how it works is that you get an X-array, which is a well-known Python library, and you need to transform it. So yeah, that basically means that we put it in the right order as depending on how our ONNX model expects it. And then, yeah, we run the model, the ONNX model, over those inputs and return it again as an X-array with the right dimensionality. The full sample basically explains how to do that. That's it, I think, for ONNX. And that's actually what our WorldCereal colleagues also use. Let me get back here. And I think this was the main part of the webinar, walking through the notebook, how to do random forest. So I'll have a look at if there are any questions and will do my best to answer them.
Thank you, Jeroen. We have a couple of questions. What is the advantage of using openEO over Planetary Computer by Microsoft?
That's a good one, actually. Planetary Computer, in its current form, it offers stack catalogs and the raw data access in the Azure cloud, right? But it doesn't necessarily offer a web service for processing itself. You on Planetary Computer, you still need to do your own processing. It does advise the use of the Pangeo ecosystem, which openEO is also very much compatible with. I showed that in the Python UDFs, we also use Xarray, and this is also what Pangeo is doing. But Pangeo doesn't offer your code as a web service. So that is for sure one thing. And another very nice feature of openEO is that we can have quite advanced processes built in. You saw in this example that I used a thing called SAR backscatter. If I would have had to do that like in real life on something like Planetary Computer, it's like weeks of work to kind of get to the point where you otherwise get with this one line. And there's other examples as well where, yeah, we really have, like, some of the processes in openEO are simple math and any library can do it, but some other things are really quite advanced. Also, how you correctly deal with loading raw data and so on. There's quite a few pitfalls that can happen. Also, when another one is when scaling up to a larger scale and you want to do it cost effectively, then the details start to matter. And then it's not so easy with a basic use of open source libraries.
Then we have the next question. Can we do cloud masking using this method provided in Google Earth Engine API?
I'm not familiar with the particular method. The CDSE doesn't have the cloud probability, but we do have alternative methods. That's one option. I would say check out our notebooks. There's a nice example of a best available pixel composite in there. And then what other people are also doing is running, again, using machine learning to classify clouds themselves. If, of course, they're not happy with the default cloud masks that are available on CDSE by default.
Then we have another question. How do you treat cloud coverage on areas with persistent clouds?
That is the most difficult problem that map makers face. That is more of a thematic question. Usually the map accuracy gets worse, right? So in those areas, the first thing is that you really need to have an as good cloud mask as possible to still retain whatever pixels that you can get. But of course, if the data isn't there, then a classifier will not magically create it for you, right? Of course, Sentinel-1 is not impacted by cloud, so there's still some hope that Sentinel-1 compensates for the lack of optical data. But if the clouds are really persistent and you do not have an optical image for a long time, then your map accuracy will suffer from that. Ellipse, the second question in that one, the ellipsoidal was answered, I think. These are processing options. So the sigma knot that openEO has is not yet radiometrically terrain corrected. It's just to the ellipsoid, but using a basic elevation model still. Only there I'm not the exact SAR backscatter expert to really give the details.
Should we run this computation on Jupyter, or can we run it on the openEO directly?
openEO can run from anything. So I used Jupyter notebooks are just convenient for webinars. A lot of people just use plain Python code, like Python scripts from their favorite IDE, and it runs from anywhere. So you do not have to be inside CDSE or whatever. Yeah, it runs from anywhere, and actually even openEO can be used also from things like the R programming language. The code that you see in the notebooks is really just defining the processing workflow. It's not the actual processing, and that is why it's technology agnostic.
Is it possible to compute vegetation indices and use them as co-predictors in the classification or regression models?
I'm not sure if I'm fully interpreting it correctly. In the example, we do already compute vegetation indices, but I'm not familiar, I have to admit, with the concept of co-predictors. So that I don't know. But questions like that, please do ask them on the forum, and then we can get an expert involved, or we can take a little bit more time to look up what you mean exactly and give a better answer.
How many hyperparameters have been considered during the classification?
We exposed a few hyperparameters, but in the example that I showed, it was only the number of trees for random forest, which we set. But this is a good one to look up in the documentation of our processes, which usually lists which hyperparameters are supported exactly.
Do you have an example of how I can fine-tune an existing model, for example, the Presto, using openEO?
No, so the fine-tuning based on Presto and so on, that is what our colleagues do actually offline, because this world of machine learning models and foundation models, it's really exploding. It's going rapid, it's going fast. There's a lot of open source stuff available out there, and in openEO we cannot, or it takes a little bit of time to standardize these processes. So for us, we can integrate them when they're standardized, but usually you really do not want to wait for us. You don't want to be blocked. And that is why our colleagues do the fine-tuning and training steps offline, especially because these extractions that I was talking about, this tabular data, it really reduces the volume of data. The raw EO data is like, it's terabytes, it's not manageable to download. But once you convert it, once you do the feature computation, or you extract data where at point locations where you have labels available, then the volume really shrinks like a lot, especially if you use something like a Parquet file to encode it. And then, training on your own hardware becomes very much feasible. And of course, what people also like to do is then use their own GPUs and so on.
Then we have another question from chat. Is VITO involved in producing ESA CCI LULC 300 meters? It seems that it is only available up to 2022. And can we use this pipeline to produce 2023 and 24? Is the model used similar to ESA CCI LULC?
VITO is not involved in that one, but I can say that we are involved in the landcover and forest monitoring service by Copernicus. This is going to be an operational service, and they intend to produce the full set of land cover maps also for recent years. The project is ongoing as we speak. For an exact timeline, I would have to refer to my colleagues. But this is happening, this is going to be there. And they recognize the problem of not having up-to-date land cover maps and aim to fill this gap with this new Copernicus service that's coming up.
Can one deduce NDVI using the tool?
Yeah, of course. That's very simple. There was an index calculation method. So if you look for the cloud masking and then the compute indices, you can compute NDVI and like 100 other indices out there. Yeah. And also much more, of course.
It seems like we have also a sub-question regarding GEE and Microsoft Planetary Computer and openEO, what is actually the difference between them?
So I would say openEO is more similar in design to GEE because we are both an API with a set of predefined processes. The key difference with GEE is this Python user-defined functions. So GEE has this limitation where you cannot use your own Python code or libraries from the Python ecosystem. And that is something that a lot of people find quite limiting. And openEO does allow this. So we're more open. Of course, we also are standardized. So I'm demonstrating the CDSE openEO, but it's a standard. So other platforms, actually just like GE, for instance, can also offer an openEO instance if they like. And then you do not every time have to learn a new platform, but can just learn the openEO standard once and the way of working once and use these multiple platforms. That is the world that we would very much like, where you stop being locked into all these APIs. The comparison with Planetary Computer, I basically just did. They are much more focused on this Pangeo library, which is open source, but it's also like a single technology, a single library that you really have to master and learn to work with, especially if you would go for generating large-scale maps. We also offer often, like within ESA projects, we also offer support packages for people that want to take on this challenge of doing it at such large scales, because it's not necessarily super easy, or people run into questions, and then we do help out there.
We are slowly getting out of time, so maybe just last two questions. Do you support other data, Landsat, Harmonized Landsat Sentinel, or only the amazing Copernicus data?
Yeah, on CDSE, we support what is available in CDSE, and they do have Landsat. This was a recent announcement, but not the full Landsat archive. That is a limitation. So I think it's like last 2 years or something. And yeah, it's a very common question. So also we are sometimes thinking how we can expand that coverage. It would be very nice if somebody offers it also as an openEO backend on USGS data, for instance, or yeah, that would really broaden the scope. And then the last question is about the statistics, if they are calculated per pixel or per segment. Here it was per pixel, but yeah, in openEO is flexible, so you can also go and compute them per segment if you need that.
Jeroen, thank you very much for your presentation, and to all of you for participating and giving us so many great questions. You're welcome to use our Copernicus Dataspace Ecosystem Forum for further questions. I would also invite you to stay tuned and follow our social media for future webinars. Thank you again, Jeroen, for your presentation, and to all of you for joining us today, and see you the next time.
Thank you.